In this tutorial, I'll build on the previous hot water loop tutorial and introduce you to air loops, which can be used to provide ventilation, heating, cooling and humidity control depending on the system type defined in DesignBuilder. I'm going to model a deliberately simple system to enable me to discuss the key elements of air loops without getting bogged down in design and configuration detail. Later tutorials will cover more complicated air loops with the capacity for more efficient operation. During this tutorial, I'll enable mechanical ventilation in the Model Data HVAC tab, show you how to add a generic air loop to provide mechanical ventilation in the system I created in the hot water loop tutorial, review the edit dialogs for the loop and system components, add the zone ventilation components, and finally I'll run a quick simulation and discuss the results with and without heat recovery. I'll start where I left off in the hot water loop tutorial, and for simplicity I'll assume that heating and mechanical ventilation is required in all zones. If I wanted to continue to naturally ventilate any of the zones, I'd add a second zone group and define different parameters for that zone. At building level, I'll switch off natural ventilation and switch on mechanical ventilation. The outdoor air definition method is set to minimum fresh air per person, which relates back to the activity tab, occupancy density, and the minimum fresh air setting of 10 litres per second per person. I'll now add a generic air loop, which is used to model standard mechanical ventilation systems. At HVAC system level, you can see that there are 4 types of air loop currently available. I'll cover the generic air loop in detail, then highlight the differences for the dual duct and unitary air loops in a separate tutorial. To add a generic air loop, I'll select it from the toolbar list with a left click, move the mouse to an appropriate position on the layout screen and left click again to confirm the position of the loop. The generic air loop contains an air handling unit, a supply air splitter, a return air mixer, and a setpoint manager. Once I've added the loop, I can amend its model data using the edit dialog. At loop level, the data is concerned with the ventilation system and its associated heating and cooling sizing parameters. The heating and cooling data is only relevant if heating and cooling coils are added to the AHU, and outside air conditions for the loop sizing are taken from the winter and summer design day data. If the auto size option is used, the system is sized by Energy Plus, and that data is then used in the simulations. Or if you have design data for the outside airflow rate, you can input that manually. The non-coincident option will size the system based on the maximum demand in each zone, regardless of when it occurs. So using this option will generally result in oversized plant. The coincident option will size the plant based on the highest coincident load for all zones, which is likely to give a more appropriate result, so I'll use that. You can size the plant based on the sensible load if the air loop is the primary form of heating and cooling, or size it on the ventilation requirement if the air loop is primarily being used to ventilate a zone which has a separate system for temperature control. I'll use the ventilation option, as I only need my constant volume air loop to meet the ventilation loads. Most of the heating and cooling inputs are straightforward, but you must ensure that you check and amend the defaults to meet your own requirement. I'm not providing a mechanical cooling capability, so don't need to worry about the cooling settings. I will need to heat the supply air to prevent cold drafts during the winter, so we'll increase the heating sizing temperature to 18 degrees C. You can select whether or not the system uses 100% outdoor air for heating and cooling sizing. If this option is set to no, the ventilation system only uses sufficient outdoor air to meet the minimum ventilation requirement. Using recirculation if the required heating or cooling airflow rates need to be greater than the ventilation flow rate required to satisfy the zone HVAC loads. In this case, I don't need to meet the zone heating and cooling loads using the AHU, so I'll leave it set at default. If the Design Day option is selected, DesignBuilder will calculate the system design heating and or cooling airflow rates using the Design Day simulation weather data. You can manually input the design airflow rates using the Flow per System option, which will feed that input into the simulation directly. All loops contain separate supply and demand subloops, which you can clearly see at loop level. The generic air loop's supply subloop contains a basic AHU with supply and extract fans and a set point manager. The AHU can be configured in a variety of ways by adding coils and heat recovery, etc., which we'll look at a little later. The demand subloop currently contains only a splitter and a mixer, but can also include supply and or return air plenum components. The splitter enables supply air connections to be made to different zone groups, in the same way that ducts can branch off from main supply ducts in real systems. And the mixer receives the air exhausted from different zone groups before returning it in a common duct to the AHU for exhaust or reconditioning. Note that I also have the additional icons available to me at this level to enable me to connect components or add a plenum or splitter. Navigating to the supply subloop allows us to access the AHU and setpoint manager components. The AHU description shows that it's a constant air volume or CAV AHU by default. Systems must be compatible in order for you to be able to connect them. So here, for example, if we had variable air volume or VAV terminal units in our zone group, we'd not be able to connect them to our constant volume AHU, as the two control types are incompatible. The AHU component diagram shows that the AHU has a supply and extract or exhaust fan by default, with airflow in and out arrows. The AHU has dampers to enable flow control on the inlet, the outlet, and also a recirculation damper, which will allow exhaust air to be recirculated where appropriate. Whilst at AHU level, I can add subcomponents. In the toolbar, I have icons for a humidifier, cooling coil, evaporative cooler, and a heating coil. To add the components, I simply select them with a left click and place them in the appropriate position in the AHU with a second left click. Here I'll select an electric heating coil component and place that before the fan. So the fan position would be termed draw through, as it draws air through the coil at negative pressure rather than blowing air through at positive pressure. The coil is now shown schematically and also here in the navigation panel. I could use exactly the same process to add any of the other subcomponents, but will stick to just the heating coil for this tutorial, giving me a heating only AHU. Going to the AHU edit dialog, I can select whether the AHU operates at constant or variable volume. So if I have a VAV system, I must change this to variable. Again, I have the auto size option for the design supply airflow rate. Note that the word supply, when used with airflow rates, refers to the total delivered air to the zone, not just outdoor air, if you have set the air loop to size on the sensible load. The availability schedule is set to on by default, which means that the AHU will always be available to meet a ventilation demand, providing it or one of its components is not scheduled off at another level. The AHU dialog is the best place to define the availability for the ventilation system. So I'll load the 8 AM to 6 PM Monday to Friday schedule. The AHU will then run only during those times to meet the ventilation demand defined in the Activity tab. The night cycle option allows the air system to cycle off when one or more zones become too hot or too cold outside of scheduled operating hours. It can be useful to prevent condensation and other problems related to cold nighttime conditions, and should not be confused with the economizer free cooling option. Night cycle operation is fully described in the help file. An extract fan is included by default, but can be deselected here. When I deselect it, the fan is removed from the schematic diagram, and Energy Plus will balance the air mass flow to and from the zones using the same return air path, which therefore must still be connected. The net effect is that there will be no energy consumption associated with an exhaust fan. I'll switch the extract fan back on. The Outdoor Air System tab enables us to define controls parameters for recirculation, an economizer, heat recovery, and any pre-treatment coils. If I switch off the recirculation option, it removes the damper between the exhaust and air inlet flows, meaning the AHU will only supply 100% outdoor air, which is what I want in this case. The outdoor air system options are covered in more detail in other tutorials, but note that the heating and cooling plant sizing calculations only include heating and cooling from the AHU coils and relevant zone equipment. They do not include the effect of other components such as heat recovery devices and economizers, or the heat gain from fans and pumps. Going to the supply fan edit dialog, which is the same for the extract fan, you can see that the fan type is fixed as the AHU is defined as constant volume. The fan efficiency is the total efficiency of the fan unit including all losses, i.e. the power delivered to the Airstream divided by the input power to the motor. If you've selected a variable volume fan, this value should be at the rated conditions. The system pressure rise is the total pressure that the fan needs to overcome to deliver air to the index point, i.e. the point with the highest pressure drop in the distribution system. Energy Plus does not currently calculate pressure rises, but uses the pressure rise data provided. For new buildings and systems, the fan efficiency and pressure rise data is likely to be available, but it's often difficult to obtain for existing buildings. Clearly, both of these inputs can have a significant impact on the fan energy consumption. If you have some information available, you may be able to calculate the missing value from this formula. If you don't have any of this data, you may be able to obtain a ballpark figure by using general fan characteristics. For example, SIBSI Guide B indicates that forward curved multi-vane fans, which are commonly found in HVAC systems, are likely to have an efficiency of 45 to 70% and be used in low to medium pressure applications, giving a maximum positive pressure somewhere between 500 and 1000 pascals. The default values are therefore a reasonable starting guide for this type of fan. A motor in Airstream value of 0 means that the motor is outside the Airstream, i.e. externally mounted, and a value of 1 means that the motor is fully in the Airstream, which applies to most AHUs. In that case, the motor will reject heat into the airflow, causing a small temperature rise, normally in the order of 1 to 2 degrees C. The AHU heating coil properties and options available will depend on the type selected, from water, electric and gas. The availability schedule defines when the coil is available. In this case, it is on, so is always available and will operate whenever a heating demand is placed on it by the AHU. The Setpoint Manager Edit dialog allows you to define the inputs used to control the supply air temperature. I have the options to change the type of controller, the control variable, and the schedule associated with that set point for the scheduled set point type. By default, the scheduled control type is selected with temperature as the control variable. The other control variables and humidity and sensible control types, including outdoor air reset, are explained in the help file and here in the info panel when selected. By clicking on the schedule, I can see the summary details here in the info panel, showing me that one temperature set point of 14 degrees C is used for all times in the year. Note that the temperature is always defined in degrees Celsius in schedules, regardless of whether SI or IP units are selected in program options. As I'm modelling a ventilation only AHU, this default set point schedule is not appropriate. Supplying air at 14 degrees C is likely to cause discomfort in winter. I could modify the existing schedule, but the DOAS schedule, or Direct Outdoor Air Supply System, has a more appropriate schedule set point of 18 degrees C, so I'll load that one. In reality, I may need to modify that schedule to reduce the set point during summer conditions and prevent unnecessary heating of cool air. Having reviewed and edited the data for the air loop and its components, I'll now add my zone ventilation components. In this tutorial, I'm modelling a very simple constant volume ventilation system, so all I need in each zone is a supply air diffuser and extract grill. In this case, I don't need any additional conditioning of the ventilation air, as an air volume sufficient only to meet the ventilation demand will be supplied to the zone at the 18 degrees C set point, and the remaining zone heating load will be met by the hot water radiators. I must navigate to one of the zones to add a zone HVAC component. So I'll just go to the first zone in the navigator list, enabling me to select the zone components. To provide supply air into my zone, I need to add an air distribution unit, or ADU. The direct air ADU enables you to supply central system air from an AHU directly to a zone without further conditioning. I can select the direct air ADU component from the info panel or toolbar, then left click again anywhere in the zone to add the component. DesignBuilder will automatically place it in the correct position on the diagram. Whenever I have a supply from an air or water loop, I need to define a return path to complete the loop and enable the fluid mass flow to be balanced in the simulation. For an air system, I simply add an extract component by left-clicking on the toolbar icon, then left-clicking again anywhere in the zone. As the direct air ADU components have editable characteristics, they're also added to the navigator list. Unlike the extract component, which is not editable and simply acts as a passive return air path. In systems incorporating direct air ADUs, if you enter your own value instead of auto-sizing the maximum central system flow rate at loop level, you must ensure that this equals the sum of the maximum zone airflow rates. The availability schedule is on continuously, so airflow through the ADUs will be governed by the other related schedules. Now that I've defined my loop and zone components, I can connect them together, having ensured that they're compatible, i.e. all constant volume in this case. When I navigate back to the air loop demand subloop, you can see that the ADU and extract component connections are now also shown. If I'd added a VAV zone ADU, which is not compatible with the AHU, then it would be greyed out to show that it's not connectable. I'll now connect the loop. After checking the schematic is correct at HVAC system level, I'm ready to run my initial test simulation. So I'll now run a quick winter design week simulation using the same parameters as the previous tutorial and go straight to the results. At building level, we can see the fuel energy consumption breakdown, the external temperature and AHU heating graphs. The fuel breakdown and AHU heating graphs show us that the AHU is operating to the 8 AM to 6 PM operating schedule set for the AHU. Looking more closely at the fuel breakdown, and switching off the gas heat generation profile, we can see that the fans operate at constant volume. throughout the operating period each day, resulting in a constant consumption profile. The electrical heat generation profile shows how much electricity is consumed at the AHU's electrical heating coil, raising the temperature of the outdoor air to the set point temperature of 18 degrees C. Going now to the ground floor west office, I can immediately see that the zone air temperatures are increasing above the set point in the afternoons, as there is no form of mechanical cooling. I can also see my constant fresh air change rate at the bottom. The heat balance graph shows a significant infiltration heat loss, but also a large amount of zone sensible cooling during occupancy. This is the cooling effect of introducing ventilation air at a lower temperature from our AHU. Whilst the zone has a heating load, the ventilation air at 18 degrees C is helping to meet that load. But once the heating load is satisfied and the ventilation air is cooler than the zone air, the ventilation system provides limited zone sensible cooling. Although the supply air and infiltration rates are constant, you may see slight variations as the zone air temperature changes, because the zone air changes are based on a reference temperature and density. I'll now enable heat recovery between the supply and exhaust airflows to see what effect this might have on the fuel consumption graphs. Going back to the fuel consumption breakdown at building level, I'll lock the y-axis and export it as a report topic to enable direct comparison. I'll name this iteration the total loss AHU, as none of the heating energy is recovered in any way. Going back to the edit screen and the AHU edit dialog, I'll enable a plate heat exchanger and leave it at default settings. Now in the AHU schematic you can see the heat recovery component with its bypass dampers. After rerunning the simulation, you can see immediately from the bottom graph that the electricity consumption at the AHU's heating coil has dropped to nearly zero, with the heat exhausted from the zone being recovered and used to heat the incoming air supply. Exporting the fuel breakdown graph again, I'll call it heat recovery, and comparing the two, I can instantly quantify the significant benefit of introducing heat recovery. The comparison also highlights that there is almost no change in the gas consumption of the hot water loop, as this is meeting the base zone heating demand, whereas the AHU coil is only being used to meet the load created by the ventilation air. In this tutorial, I've used a very basic constant volume ventilation system to explain the key points relating to modelling air loops in DesignBuilder. Clearly, there are more efficient ways of providing ventilation, often by varying the volume of the air supply, which is discussed in other tutorials.